Hey everyone, and welcome. Today we are going on this incredible journey, not out into space, but deep, deep into the heart of our own planet. And you know what our guides are for this trip? The super powerful waves generated by an earthquake. So let's just start with the big question, right? How on earth do we know what's at the center of our planet? I mean, think about it. We've sent probes to the absolute edge of our solar system, but the deepest hole we've ever managed to drill, it only gets us about 0.2% of the way to the core. So how do we have this amazingly detailed map of what's down there? Well, the answer, and this is what's so cool, isn't about digging at all. It's about listening. Every single time the Earth shakes, it's basically sending a message from the inside out. And over the years, scientists have gotten really good at being planetary detectives, piecing together the story that these seismic waves are telling. Okay, so to understand this message, this story from the deep, we've got to go right to the beginning, to the exact moment that rumble begins. Every earthquake kicks off at a single point deep inside the Earth's crust. That spot is called the focus. That's where all the energy is first released. And the spot directly above it, right on the surface where you and I live, that's what we all know as the epicenter. And this is just the perfect way to picture how that energy travels. Imagine tossing a rock into a perfectly still lake. You see those ripples spread out in every direction, right? Well, an earthquake's focus is just like that rock, and the seismic waves are the ripples. Except, and this is the crazy part, they're traveling through solid rock, not water. Now, these waves, they're not all the same. They pretty much belong to two main families. First, you've got body waves. These are the messengers from the deep. They travel right through the body of the Earth. Then, when those body waves finally hit the surface, they create a whole new set of waves called surface waves, which, as the name suggests, travel along the surface. They're slower, but they are the ones that cause most of the damage. All right, let's zoom in on those body waves first. You can think of them as the first responders. They're the ones carrying the initial crucial clues from deep inside the planet. And in this family, there are two main players. You've got P waves and S waves. P stands for primary, and that's because they are the fastest. They move by compressing and expanding the ground, kind of like an accordion. Then you have S for secondary. They're a bit slower, and they move the ground from side to side. But here, right here, is the most important difference. P waves can blast through anything, solids, liquids, gases, you name it. S waves, though, they can only travel through solids. And that one little fact, well, it's the key to this whole mystery. And when we say P waves are fast, we are not kidding. These things are screaming through the Earth's interior at up to 15 kilometers per second. They are the absolute scouts of any earthquake, the very first signal that anything has happened at all. And you can see that difference in motion perfectly right here. The P wave on the left, it's like pushing a slinky. See how the compression just travels down its length? Now the S wave on the right is more like flicking a rope. The wave itself moves forward, sure, but the rope moves up and down. That side-to-side shearing motion is what makes S waves so unique. So let's just hammer this point home because it is so important. That shearing motion of an S wave, it just doesn't work in a fluid. I mean, you can't really shear water side to side, right? It just flows. So this inability to pass through liquids is the single biggest clue these waves give us about what our planet is made of. Okay, so once those body waves have raced through the planet and they finally reach the surface, they give birth to a whole new crew of waves. And these are the heavy hitters. These are the surface waves, and they have names like love waves and Rayleigh waves. Like their name says, they're pretty much stuck on the surface. They move way slower than P or S waves, but because all of their energy is concentrated right up here where we live, they are by far the most destructive. And just to put a number on it, these L waves clock in at around 3.5 kilometers per second. Now that sounds fast, but remember those P waves? This is way, way slower. And that difference in speed, that's what sets the stage for a race. And that's really what it is. Every single earthquake kicks off this massive planet-scale race. You've got each type of wave traveling a different path, all at their own unique speeds. And this right here, this is the finish line. A seismograph is basically a super sensitive instrument that records the ground shaking. The chart it spits out, called a seismogram, is like a photo finish of that wave race. You can literally see the exact moment each type of wave crosses the finish line at the detector station. And the order of arrival is always the same no matter what. First, you get a little jolt. That's the super fast P wave showing up. Then, a few seconds, or maybe even minutes later, the stronger S waves arrive. And finally, the rolling, destructive surface waves make their appearance. And that's when you get the most violent shaking. Okay, so we've got this race. We've got the arrival times recorded all over the globe. Now, it's time for the payoff. What does all of this actually tell us? I mean, it's a totally fair question. How do we get from a bunch of squiggly lines on a piece of paper to this incredibly detailed, layered map of a planet that no one has ever seen the inside of? Well, the answer lies in the shadows. Yeah, seriously, it turns out that there are certain parts of the planet where seismographs won't detect certain waves from an earthquake at all. These dead zones are called shadow zones, and they are the final, crucial piece of the puzzle. So here it is, the big reveal. There is a huge shadow zone for S waves. If an earthquake happens on one side of the planet, S waves are never, ever detected on the other side. So why? It's because to get there, they'd have to pass through the Earth's core. And the moment they hit that outer core, they just stop. Remember their critical weakness, their inability to travel through liquid? That becomes the scientist's greatest strength. That massive shadow is the smoking gun, the definitive proof that our planet has a molten liquid outer core. So by just listening to the story these waves tell, we mapped a place we can never ever visit. It really makes you wonder, doesn't it? From the rumbles of our own planet to the gravitational waves rippling from distant black holes colliding, what other secrets of the universe are just out there, hidden in the waves, waiting for us to learn how to listen?